All right, so we continue from where we left off. So we were looking at two-level minimization in the sense that our expression, Boolean expression, is in the form of sum of products, and what we are looking for is, again, the goal of minimization is to minimize area and delay, and at the Boolean expression level, what it translates into is we minimize the number of product terms, and also within the product term, we minimize the number of literals that are there. All right. So these are the two goals of two-level minimization, and the principle that we use for carrying out minimization is this simple principle here, that xy plus xy bar is basically equal to x here. And if we perform this particular operation on our Boolean expression, then as you can note here, from combining these two expressions, the product terms have been reduced to 1, and the literals in each one of those terms has been reduced to 1 here. So that's the basic principle. And we were saying, we all know this, that the method that we commonly use to apply this particular principle is the K-map, where we represent the data in this form of a table, and which helps us to apply this particular principle here. But we also noted that as the circuit or the circuit complexity increases, or the Boolean expression becomes more complicated, drawing a K-map for larger number of variables and carrying out this operation becomes difficult, and the whole process in some sense has to be automated. And what we are looking, so it's all about how do we carry out the task that we are familiar with in many of these cases, but on a much larger scale. And therefore, we want to look at a problem or a solution to a problem which scales with the problem size, maybe of the same order n. You know, if you double the circuit complexity, our method also doubles in terms of effort required. It does not become, if you double the circuit complexity, our method doesn't become 9 times more difficult to, or exponentially more difficult to apply. So what, in general, the method that you're looking for should scale linearly with the complexity of the issue here. All right. So again, K-map, as we said. So let's look at a alternative method where you don't have to represent it in the form of a table and visually look at which terms you can combine, which terms you cannot. So this is a method, Cohen-Miklaski method here. So let's look at what this particular method, how this particular method carries out the minimization process. There are when you look into this particular method, there are a couple of definitions with which we have to become familiar. The first one is you'll hear the word implicant. Now, so implicant is, you know, each one of those terms for which the output is 1. Okay, so this is an implicant here. So you can say x, if you look at the first term here, x bar, q1 bar, q0 bar is an implicant, is a term for which the output is 1. Similarly, we have here 5 implicants, 1, 2, 3, 4, 5. So that's basically the terms for which the output is 1 is called an implicant here. All right. I have a set of implicants, 1, 2, 3, 4, 5, which describes the my function. Okay. So any function, any Boolean function would be a set of implicants. All right. So that's clear. Now, also note that when we apply our principle x plus x bar equal to 1, what we are doing is we are trying to grow the implicants here, right? We are taking one implicant and combining it with another implicant. So that process is called growing an implicant. You're encircling 2 of them and constructing a new implicant. So for example, when I encircle this, I combine this implicant and this implicant, and I generate a new implicant here, which is A. Similarly, I combine these 2 implicants and I generate a new implicant, which is B, and so on and so forth. Right? So what we are doing is combining implicants, and this process is called growing the implicants. And the idea is to combine them such that they cannot be combined any further. Right? So to make the largest possible, you take an implicant, combine it with as many as possible, and combine them in what form? I mean, we know that combining them in the form of x plus x bar equal to 1, that principle. Okay? So we combine them in such a way we try to make the implicant as large as possible. So this is called like taking an implicant and growing it and making it as large as possible. And an implicant which cannot be combined with any other implicant. Once that particular process ceases, you get what I call prime implicants. Okay. So in this case, for example, when we take this one and we combine them together, we get an implicant A, and we note that this can't be combined with anyone else. Any other implicant or whatever, it can't be combined. So we will call this as a prime implicant A. And similarly, you have a prime implicant B, and a prime implicant C, and a prime implicant D. Right? So K-map, if you think of K-map, what you're trying to do is from the set of ones that are given to you, you're trying, first of all, by combining, we all know that we try to combine. So what you're trying to do is get a set of prime implicants. That's what, in the alternative terminology, you're trying to generate a set of prime implicants from the original set of implicants. Okay? So that's the first step. Combining implicants to generate a set of prime implicants. So that's what you're doing in a K-map. The next thing is, out of these various prime implicants that you see here, some of them are essential prime implicants. What do I mean by that? For example, if you look at A covers a term. It covers a term, this particular term, which no other prime implicant covers. Right? If you look at B doesn't cover this. If you look at C, doesn't cover this. D doesn't cover this. Right? So A covers a term. If you note that A is a prime implicant, it covers these two terms here, one and this one. Right? The circle is drawn around these two. So it's sort of covering these two. But A happens to cover a term which no other prime implicant covers. And we call such a prime implicant, obviously, essential prime implicant. I have to keep them in my eventual solution. Because if I don't keep in my eventual solution, obviously then I'm not covering this particular term here. Right? So a prime implicant which covers a term which no other prime implicant covers is called essential prime implicant. So we can see here, obviously, A is a essential prime implicant. B is not an essential prime implicant because B covers this term which A also covers. B covers this term which C also covers. So B is not a essential prime implicant. C is also not an essential prime implicant. D is an essential prime implicant. It covers a term here which no other term covers here, right? So what we do is we have two EPIs, essential prime implicant, A and D, which means that in our eventual solution, A and D have to be there. And besides that, I may have others also. Okay, but A and D are essential to my solution here. Okay, so these are, implicant, prime implicant, and the essential prime implicant. These are three new terms for you. And of course, what is two-level minimization? Two-level minimization is cover the set of those ones that were there with as few PIs as possible. Because each PI, remember, prime implicant represents a term, product term, right? So you would like to cover it with as few PIs as possible here. So our method, the same K-map method can be rephrased as find all the prime implicants and find a minimum set of PIs that cover the onset, right? So by encircling, what we are doing is we are finding the largest encirclement. After carrying this out, we are finding the set of prime implicants, which we have done, A, B, C, and D. And then what we have to do is, out of this A, B, C, D, we have to find a minimum set of PIs. Out of A, B, C, D, we have to choose a minimum set, number of these prime implicants, such that all the ones are covered. All the ones are covered. Now, in this process, we have found that two of them are essential prime implicants, which means I have to keep that in mind. So A has to be kept and D has to be kept, right? Which means that when I keep A, it covers these two terms. When I keep D, it covers these two terms. So the only two terms that are left, only term which is left here. So these two are covered. These two are covered. The only term which is not covered is this one, right? So my set possibilities are AD I have to keep. I could use B to cover this one, or I could use C to cover this particular one. And both of them at this stage at least are equivalent because both of them are this. All right, so this is the process. Find a set of prime implicants and then find a minimum set of prime implicants to cover the set of ones that are there. And this process is helped if you beforehand, if you find out what are the essential prime implicants. So first of all, you keep those and then look for ways to cover the ones which are not covered by the essential prime implicant. Okay, so the same thing, we do it in a K-map. The same thing can be done by many alternative means. And the whole idea is that you do it in a way such that as the size of the problem increases, the complexity of the algorithm doesn't increase, and doesn't become unmanageable. Okay. So one such method is what we are calling is the same process, the McCluskey method, Cohen-McCluskey method. So this is the onset of a function. So I have a 4 variable Boolean function. And these are the terms, these are the implicants for which my output is 1. 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1. So for all these terms, my output is 1. All right. So obviously we give them names 0 here by its decimal equivalent 5, 7, 8, 9, and all that helps. So what is the first step now? Given this particular set, what do I have to do? Construct a set of prime implicants. And how do I construct prime implicants? I start combining. I have to combine them, right? So how do I combine them? Well, I start with the first entry here and I check, can it be combined with 5? Now, what do I mean by combining? That the two terms should differ in only one bit. Two terms should differ in only one bit. In one case, let's say that bit is 0. In the other case, the bit is 1. That's what the x plus x bar equal to 1 means here. So I see here 0 and 5. Can it be combined? No, they differ in too many things. 0 and 5 cannot be combined. 0 and 7 can't be combined. 0 and 8, yes, it can be combined, right? So 0 and 8, if I combine, what do I get? So when you combine, when this term is 0 and this term is 1, they cancel out, right? They cancel out. That particular term is no longer there and 0, 0, 0 is there. Okay, that's what combining means. That particular term, it will, when you combine those two terms, x plus x bar, that term will disappear. What if, let's say this function was x1, x2, x3, x4, when I write it like this, x1 is no longer there. It's been eliminated. And all that you get is x2 bar, x3 bar, x4 bar. Okay, so I combine 0 and 8, and then like that you see, so I've written that this is a new implicant. It's a larger implicant. I don't know whether it's a prime implicant. Prime implicant means it cannot be combined any further, right? So I don't know whether it's a prime implicant yet, but I've sort of grown my implicant to this stage here, 0 and 8, and I need to look at 0 and 9. Can it be combined? 0 and 10, 0 and 11, 0 and 14, and you find you can't combine any of them, right? You note that to combine, they have to differ in one bit. So I'm finished with this particular entry. Then I go to the second one. Can 5 be combined with something? 5 can be combined with 7. So note that when I combine the bit which differs, that gets eliminated. So I get 0, 1 and 1 here. And I've combined 5 and 7. I note it down, right? And then 5 and anything else? Well, you scan your table. So what you do is pairwise keep examining 5 and 7, 5 and 8, 5 and 9 and all that, and you go through and you find, well, maybe it can't be combined. Then you look at 7 and 7 versus others. 7 and 15 can be combined. 7 and 15 can be combined, so we get this, and like that you fill up the table. Okay, so you go one pass over your the entire set of implicants. You go one pass, you see whether it can be combined and all that, and you arrive at this one. That's the first pass. Now what you do is you work on these. Can the first one be combined with the second one? Can the first one be combined with the third one? Can the first one be combined with the fourth one? And you keep on seeing whether it can be combined or not, right? So this is now, so earlier we were working on this table, now we work on this, and we see whether they can be combined or not. So note that if I look at it, this can't be combined with anything else. So I keep it as it is, 0 and 8. We sometimes give it a symbolic name also. It helps all the time calling it 0 and 8, symbolic name A. Well, 5, 7 and this, can the second one be combined with something? They have to differ in one bit. So I keep it as it is. Third one, Keep it as it is. Note this one, 8, 9, and 10 and 11. 8, 9, and which one am I combining? This one, right? No, which one? 10 and 11, right? So these two, correct? Note that this and this can be combined because 1 0 is same, 1 0 is same. These have already been eliminated. This is 0 and this is 1. So 8, 10, 9, and 11. These can be combined together. So I get this new implicant, which is D. And similarly, you can note 10, 11, 14, 15, 10, 11, 14, 15. Right? So these can be combined here. 10, 11, 14, and 15. Right? So I look at it and see which all can be combined. Right? Which all can be combined, and these are higher level implicants. The larger the implicant, prime implicant, the less the number of terms in it. Right? So that's the larger implicant here. This is larger than this particular one. I mean, or smaller in complexity as compared to this one. Okay. So can you see that all of them, when I go through this particular pass, after that you can see nothing else can be combined. I can't take this term and combine this term or combine this term or not. Nothing can be combined any further. Which means that these A, B, C, D, E are my prime implicants. They can't be combined any further. And so I found a set of prime implicants for my Boolean function. Okay. And you can note that they cover all the terms that were there. 8, 9, 10, 11, 10, 11, 14, 15, they cover all the terms. Everything is covered. Now the process, so we have all these prime implicants that are there. Now out of these prime implicants, the next step is we have to find which one is essential to my solution. And after essential, then we have to decide which one out of these, which one to use to cover the whole set that is there here. So for example, we are looking for a minimal cover here. So what I've done is all these implicants that were there, I've written them out 0, 5, 7, 8, 9, 10, 15. And we have found 5 prime implicants. We've written these down here, A, B, C, D, E. And in the form of a table, I'm just saying A, the prime implicant covers which one terms here. So A covers 0 and 8. Go back and see. A covers 0 and 8. Right? So that is indicated, 0 and 8. B covers 5 and 7. C covers 7 and 15. D covers, note that, go back and see the D part here. D covers 8, 9, 10, 11. Right? So I fill this up. D covers 8, 9, 10, and 11. And E covers 10, 11, this one. All right, the same information is displayed in this form of a table here. Now, I'm showing it in the form of a table, but note that each one of those steps are simple, and these all can be automated. All right. So now, is there any essential prime implicant? A covers a term 0, which no other prime implicant covers. So A is essential to me. Okay. So basically what you are looking for is find single entry rows. A row which has a single entry. That is what will classify as prime implicant. If a row has more than one entry, it means there are more than one prime implicants covering it. Right? So we are looking for single entry. So single entries are A is there, and what else? This one is also there, B. And so one is A, of course, is essential. Essential means I'll have to keep it, right, in my cover. If I have to keep it, A will have to be there in my solution. And A covers what? 0, and it also covers 8, which means I don't have to bother about 0 and 8 anymore. So I eliminate 0 and eliminate 8 also, because I have to keep A in my solution. And A covers those 0 and 8. So I don't have to bother with 0 and 8. Anything else which is B is also essential to my solution. So I keep B here, and B covers 5, and B covers 7. So I eliminate 5. I don't have to bother about 5, and I don't have to bother about 7. So that's gone. Now, out of all these, anything else which is essential? We see D. Huh? Or C, either way. So D is here. D covers this one, which no other term covers here. So I have to keep this. And then D also covers these two. So I have to eliminate these also. I don't need, these terms are already covered. Now I'm left with here. And which is essential? E. E is essential. So this one, and then this covers this one also. So I'm left with, I've covered all the terms that are there. And the solution that I'm done with is ABDE. All right. So ABDE is the solution to my minimized solution to my Boolean expression here. All right. Let's look at the another example. Example number 2. So let's say there is some. So now remember, after the first step is taking a Boolean expression and converting it into finding a set of prime implicants A, B, C, D, E, and they will cover your min terms or the in some form, right? So let's say we've gone through the first step and we've arrived at this particular table here. A, B, C, D are my prime implicants, and they cover these particular terms here. M1, M2, M3. These could be 4 variable, 5 variable, 6 variable. We're not bothered anymore. We just represented it in the form of a symbolic form. All right. So here, any essential prime implicants? Any essential prime implicants? No. So what do we do now? No essential prime implicants? Huh? Okay, so here, note, now let's look at, so there are some ways of simplifying our approach here. Look at M1 and M6. Let's examine these two rows, M1 and M6. The method says row 6 dominates row 1. Dominates in the sense that every term that is there in row 6 is also there in M1, but there is something in this row 6 which is not there in M1. So row 6 dominates row 1. Correct? So that definition is clear. Row 6 dominates row 1. And it says if row 6 dominates row 1, remove row 6. Remove row 6. Now what is the idea? The idea is that, let's say, if you look at row 1 and row 6, I will try to cover row 1 by using what? Either A or B. Either A or B. And if I do that A or B, it will also cover M6. But if I go the other way, I can cover my M6 by E, but then I will not be covering M1. So you are seeing that if one row dominates the other, then the less dominating one, if I cover that, I'm making sure that I'm covering this also. If I cover this particular min term M1, I'll end up covering this one. But the reverse is not true. If I cover this, I could cover it with E. But then M1 will not be covered. So what I'm saying is if one row dominates the other, the dominating row you can remove from your table. That row you can remove. Okay? So this one is gone. No longer required. Because by covering this, you will automatically cover the last row also. Is there another row which dominates? M4 dominates what? M4 dominates M5. So what happens? M4 goes. Right? M4 dominates M5. M4 goes. So you get a reduced table now. By looking at row dominance, you get a reduced table now. Now, is there an essential prime implicant? So let's take this table now. It's a reduced table. Let's take this table. And now look at this. Column B dominates column A. So after looking at rows, column B dominates column A. Agreed? It covers, the terms that are here. And it also has this. Column B dominates A. It says remove column A. Column dominance. Remove column A. Make sense or not? Remove column A. So this has, B is covering what? M1 and M3. And A is covering only M1. So if I eliminate A, It doesn't matter. B is covering M1 and is also covering something else, M3. On the other hand, if I eliminate A, then on the other hand, if I eliminate B, then I'm in trouble. Right? So it says if there is column dominance, column B dominates column A, column D dominates column E, eliminate the other column here. Eliminate it here, and we have column D which dominates column E, eliminate it here. Gone. Right? So our table becomes even simpler. Now, do I have essential prime implicant? B becomes essential. B becomes essential. D becomes essential. And then, so B is essential. So eliminate this also. It covers this also. And now we compare this. D is this one here, covers this and covers this over. So B and D are the solution. B and D are the solution to our problem here. The optimal solution to our original expression is B and D. Okay, so first one is, you use the concept of essential prime implicant, you keep it, and you find after that the table simplifies and you're able to arrive at the solution. Sometimes there are no essential prime implicants, then you use the concept of row dominance and column dominance and simplify your table. And you simplify your table and you find that if you apply the rules, you now find some are essential to your solution and you're able to again, arrive at the solution that is there here. Okay, BD essential, and therefore we find cover is B and D. All right. So suppose I've done essential prime implicants. I've done row dominance, column dominance, and after doing all this is the table I'm left with. You can check. There is no row dominance. There's no column dominance. There's no essential prime implicant. Nothing in this particular table now. All right. So nothing is left in this particular table here. So now how do I proceed? How do I start? Now remember, these are only simple problems. So how do I start? It may be that final solution may have only 2 of them or 3 of them. Right? So how do I start? Where do I start? What do I do? All the tricks that we had, dominance and all that, essential, everything eliminated now. Now we are left with this final kind of a table. And we still have to find a minimum set. Huh? So now you're saying some heuristics, some things which appear to make sense. Maybe a column which covers a large number of min terms, I should keep it. If there is a column here which covers, let's say, 4 min terms, and all of them cover 2, 3 or whatever, then I'll think maybe A is, I should keep A. But in this case, each one of them covers 2. Or this one, C and F covers 3 of them, right? C covers 3 and F covers 3. So you may think, well, C, let me keep it, right? So, there is no principle that you're using, is just a feeling that maybe it's a good way of doing it, right? So when we have rules like that, we call them heuristics. We see that you apply that particular rule, it seems to make common sense and that. But before we jump into that, suppose I do want to solve in a slightly more rigorous manner. What do I do? Well, we do the following. We search. We search our table. We search our table. We say, you see, we start with this. We start from here. What are the options that I have? Include A. Either in my final solution, A will be there or A will not be there. Right? Similarly, in my final solution, B will be there or B will not be there. C will be there or C will not be there. So I have to sort of search, right? So my options are include A or discard A. Then at the next point, if I go along this particular branch, I will say include A, include B or discard B. And then like that, I will keep on going. But you can see the search will, as the number of terms increases, the search becomes very difficult. Okay? Search becomes very difficult. But suppose we do say include A. Let's say we go along this particular path, include A. All right? Which means I will what happens? So if I include A, I will keep A in my solution, right? So A is in my solution. So what do? I eliminate A and all the terms that A covers. So I'm going to include A. A covers M0 and A covers M1. Right? Now I look at the table. Can I quickly now find essential prime implicants and all of that and get a solution? Is there anything which is essential? A, if you look at anything which is essential, we've eliminated these two. So our table becomes, if you note, our table becomes B, C, D, E, F. It becomes this. A I included, and I'm saying C and D. Does it make sense? Huh? C and D is a possible solution, right? C covers, but how did I arrive at C and D? C dominates. C dominates E, right? So I can eliminate E. E is no longer there, and all right. So it makes sense. You can apply. So now the idea is once you include A, the table simplifies. And then you may find that you get something essential prime implicant or row dominance, column dominance, and all of that, and you arrive at a solution, ACD. But the issue is this minimal? Maybe I could do it with 2, right? So I don't know if it is minimal. So I went along this path and I say, well, I got a solution, right? But the question that we need to ask is this minimal? So the minimal means to justify that, I have to go along this path. And suppose I discard A. But then after discarding A, do I have to find another solution? That will become too much, right? At every stage, if you find the whole final solution and then, you generate all possible solutions and you compare them, that's a kind of an exponential complexity technique. That you generate all possible solutions and then you compare. You have to stop here. So suppose I discard A. So the idea is that the search along any branch may be terminated if we can predict that solutions obtained by following that branch will have either the same or larger number of PI than the best solution found so far. Correct? I found a solution here. If I can say, if I go along this particular path without actually finding the solution, if I can predict that the solution will have either the same number of prime implicants or more, if I can just say that much, not the solution, but if I can say it will have at least 3 or at least 4 implicants. Suppose I find that if I go along that path, this particular path will have at least 3 prime implicants. Then I don't need to go and find the solution. I already have a solution with 3. I don't need to go here. This itself is optimal. Okay. So the idea is, okay, let's discard A. And at this stage, we don't solve it. We just try to predict our final solution is going to be how many, at least minimum. We can't say, exact number of prime implicants that it will have. But maybe we can say that this is the minimum that my solution will have. Okay, how do we say that? Okay, so let's say this was our table here. And what we do is we discard A. So we discard A, right? We discard A, but remember when we discard A, we don't discard M0 and M1. Discarding means A is not going to be there in my solution. So M0 and M1 will have to be covered by some other implicants, prime implicants then. So I discard this. Okay. So let's look at the reduced table here. This is my table here. So I'm at this stage here. I've discarded A and I'm here. I'm not going to solve it. Maybe I can solve it at this stage, but that's not our interest. Our interest is to predict what is the minimum number of PIs that this particular path will give me. So the idea is the following. Minimum PI will be number of pairwise independent rows in the prime implicant table. Number of pairwise independent rows in the prime implicant table. All right. So which rows are pairwise independent? If you compare M0 and M1. So note that row 1, 4 and 8 are pairwise implicant. Row 1 and 4 and 8. So if I look at 1 is here, 4 is here. Pairwise independent, correct? Nothing common in between them. If I look at 4 and 0, these are not pairwise independent. 1, 4 and 8. If you look at 8, 1, 4 and 8. How many rows are, you can say they're all pairwise independent. 1 and 4 are independent, 1 and 8 are independent, 4 and 8 are independent. How many such rows are there that you can say are pairwise independent? A set of rows, and any two rows, if you examine, are pairwise independent. This is clear? 1, 4 and 8? 8 and 4 you compare, independent. 8 and 1 you compare, independent. So you search your table and you say how many such rows you can find which are pairwise independent. And then it says if you have 3 rows, you will require at least 3 PIs. Minimum of 3 PIs to cover, because they are pairwise independent. For example, if I look at 1 and 4, 1 and 4, they are pairwise independent, which means I will have to find a prime implicant which covers this one, which will not be covering this. So the number of pairwise independent rows tells me that I must need at least that many PIs, at least that many prime implicants. Okay, 1, 4 and 8, I must have at least 3 PIs. I may be requiring 4 PIs, that I cannot tell. Unless I solve, I may find I require 4 PIs. But at least the minimum I can tell by looking at pairwise independent rows. So if what is happening is I discarded A, and at this stage I find there are 3 pairwise independent rows. So I know that any solution along this particular path will have at least 3 PIs. And therefore, it's not worth following that particular path. I can neglect all this particular path here, and I should go along this particular path. Okay, so this helps in going through the branching, whether I should follow that particular branch or I should not follow that particular branch. Okay, all right. So, now it becomes a question of a search algorithm. How do I search? How do I search my table and arrive at an optimal solution? Okay, so these are, this one way, there are other ways of doing it here. Now the issue was, we said, okay, we started by saying include A or discard A. Well, we could have said include B or discard B. Include C, we could have started with include D or discard D. Where do we start? What should be our starting point? Which one to include? Because, when I look at the table, it doesn't seem that all of them, it doesn't seem that anyone is essential. We don't have any essential prime implicant. So we could start with any. So again, what we have is a set of heuristics. Find these, a common heuristic is find the set of columns that cover the pairwise independent rows. So at any stage, let's say, which one to choose, include A or B or discard A or B or C or whatever. Find the set of columns that cover the pairwise independent rows. Select the column that covers the maximum number of rows. Okay, so let's explain. Pairwise independent rows, we had already found 1, 4, 8. All right, 1, 4, 8 are pairwise independent. Who covers 1? Row 1 is covered by, let's look at 1. 1 is covered by A and 1 is covered by F. All right. Row 4 is covered by C and E. Row 8 is covered by B and D. Now it says you found all these columns are of interest. So you find pairwise independent. Why pairwise independent? Because those are essential. I have to cover those. Okay, so pairwise independent rows are important for us. So now I have to choose amongst them. Which one should I start with? Choose amongst them. And how do you choose? So you have a choice between starting your search with A, B, C. So A covers 2 rows, F covers 3 rows, C covers 3 rows, E2, B2, and D2. So where do we start? It says you could start your search algorithm with F or a C. Start with these two. These two, it's a heuristic. So it says start with either, so you say include F or discard F. You start with that. Or you say include C or discard C. It says don't start with A. Okay. So if we choose C, we get a solution CAD. You can go through the process. So the other point was, instead of using the exact branch and bound procedure, which is time consuming, one can use the above heuristic repeatedly to select columns to include in the cover. Remember, the searching is, again, if as things become complex, searching will require time. So what do we do? Well, for example, we said, how do you choose a column to include or not include? So this is the heuristic. So you keep on using this particular heuristic. So instead of using exact branch and bound procedure, use the above heuristic repeatedly to select columns to include in the cover. So you start by looking at pairwise independent rows and all that, and then see the column which covers the most number of rows, include it in your solution, and then simplify the table. Maybe after simplifying the table, you get essential, row dominance, column dominance, and you get a solution. If you don't get a solution, again look at pairwise independent rows and find a column which covers the most number of rows. Include it in your solution. And then look at, maybe the table simplifies and you get a solution. If you don't, keep on doing it. Okay. So that's a simple heuristic where you don't really have to search the table in a more rigorous manner, and so many of the algorithms that you find, if you try to do it in a rigorous manner, it becomes very difficult. And throughout VLSI, in all this algorithms and all that, you'll find that there are these heuristics that are used, heuristics to simplify the this one here. The next problem is, which we'll not go into. So let's say you've obtained the minimal two-level Boolean expression, right? You've already taken an expression, sum of products expression, and minimized it. It's already minimized. And we said one way of implementing is here. But the other way, I'll just show you two ways of implementing. Same expression, two ways of implementing. This is a two-level representation of the circuit, where if you count, you require 6 3-input AND gates, 1 7-input OR gates, and if you count the wires, all these 1, 2, 3, 4, and so many wires here, and then internal wires, 25 wires. Wires also consume area. So if you look at this solution, and then you look at this solution, there's also the same expression, but represented in this form. You require 2 3-input gates, 2 2-input gates, 11 wires. Just look at this solution versus this solution. Same minimized Boolean expression. And just look at the difference in terms of the complexity here and the complexity. Which means what? After doing your Boolean expression, and basically this is what a two-level expression is, sum of products form. What you need to do is, if you want to go from here to here, what you need to do is take your Boolean expression and factorize it. Factorize it. And when you factorize it, you can represent in this form, multi-level form. So a very, very important step is to take a two-level representation and convert it into a multi-level representation. And the essential process involved is factoring. So very quickly, we'll look at that. So that's the next step in logic synthesis. You factorize your Boolean expression to arrive at this. And then finally decide which are the optimum set of gates that I can use now to implement my solution. Okay, so let's stop.